Okay, so we're going to start talking about our real-world application of implicit differentiation. And we're going to talk about what are called related rates. So there's certain words that indicate to you that you're talking about change. Some of those words might be increasing, decreasing, growing, shrinking, all those kinds of words. And in the real world, change occurs over time. So when we talk about how a quantity changes, we're talking about the derivative of that quantity with respect to time. So in real world applications, a lot of times what we're respecting when we take the derivatives is time. So just to kind of get you familiar with some of the notation you're going to see, example 1 says, write the following statements mathematically. So John is growing at the rate of 3 inches per year. How you can write this mathematically is we can say that John's height is changing with respect to time. And so we can call that dh dt. That means the change in his height with respect to the change in time is positive, since he's growing, 3 inches per year. So John's height changes with respect to time at a rate of 3 inches per year. dh dt is a rate, and so this is telling what that is. So the next one, my mutual fund is shrinking by 4 cents per day. I don't really have a standard variable for mutual fund like we do for height. I'll just call it M. So we'll say the change in my mutual fund with respect to time. Shrinking means it's negative 4 cents per day. That's how you can mathematically say that, right? The radius of a circle is increasing by 4 feet per hour. So the radius is changing. So the rate that it's changing is what we're talking about. So the rate of change of the radius with respect to time. Increasing means it's positive 4 feet per hour. And the volume of a cone is decreasing by 2 cubic inches per second. So the volume is changing. They're giving me the rate that the volume is changing. So the rate of change of the volume with respect to time. Decreasing means negative 2 cubic inches per second. That's just how you would write some of those statements in mathematical terms using a derivative. Since we're talking about a rate of change, we can talk about it in terms of a derivative. Okay, so let's look at some examples of some problems that you would do where you would be finding information like that. So let's look at example 2. A rectangle is 10 inches by 6 inches whose sides are changing. Write the formula for both the perimeter and area and how fast each is changing in terms of L and W. It's kind of tempting because it says it's 10 inches by 6 inches, but those dimensions are changing. So those don't really mean a whole lot to us right now because they're both changing. They're not constant. So we know that the perimeter of a rectangle is 2 lengths plus 2 widths. So if you were to take the derivative of that with respect to time, you would get dp dt, the rate of change of the perimeter with respect to time, is 2 dl dt, the derivative of L is 2 dl dt, plus 2 dw dt. All right, then area of a rectangle is length times width. And so for the change in the area, we would get dA dt equals. Now you have to use the product rule on this one because you do have L times W. So you would do first D last plus last D first. Right? Okay, so now let's look at these. So now we have these formulas that relate these rates of change to each other. So we can use these to find stuff out. So let's look at example 2a. So its length and width are increasing at a rate of 2 inches per second. That means that dl dt and dw dt are both positive 2 inches per second. Increasing means positive, and that's telling me the rate that the length and width are changing. So that's dl dt and dw dt. So you can plug that in and figure out the change in the perimeter and the change in area for those rates of change. So the change in the perimeter is 2 times dl dt plus 2 times dw dt. So it would be 8. And it's going to be inches per second. Perimeter is measured in inches. So the change in perimeter would be measured in inches per second. The change in area, we would use our change in area formula that we found up here. dA dt is equal to the length times the change in the width. So the length was 10 inches up here. And the change in the width was 2. Plus the width, which was 6 inches, times the change in the length, which was 2 inches per second. So this is going to be 20 plus 12. This is going to be 32 inches squared per second. Right. Area is measured in inches squared. If you look at your units on what you just multiplied here, you had 10 inches times 2 inches per second. That's inches squared per second. And then 6 inches times 2 inches per second, that's 12 inches squared per second. So it's inches squared per second as units. All right, I'm not going to do part B. You can try part B on your own. The only difference on part B is that the length and width are decreasing. So dL dt and dW dt are both negative 2 inches per second. If you go back and plug into your formulas again, you should see that the only difference in terms of your answer is now both of these will be negative. It doesn't always work that way, but in this case, it does work out that changing the rate to a decreasing rate instead of an increasing rate just changes your answers to decreasing instead of increasing. Something more interesting happens when you look at the length and width changing at different rates. So that's what's happening on parts C and D. Again, you're just plugging into the two formulas we wrote up here, the change in perimeter formula and the change in area formula. But now dL dt and dW dt are not the same. So like on part C, the length increases 3 inches per second. The width decreases 3 inches per second. So dL dt is positive 3 inches per second, but dW dt is negative 3 inches per second. So you can plug in and see what happens there. The effect it has on the perimeter in that case is that there is no net change in the perimeter. But there will be a net change in the area if you use these values up here. Okay, so you can go through and try those. I'll write down what the answers are. Okay, so if you plug into those two formulas we wrote for change in perimeter and change in area, on this one here it says length is increasing 3 inches per second. That means dL dt and it's positive. Width is decreasing, so that's dW dt and it's negative. All right. Length is decreasing, so that's dL dt and it's negative. Width is increasing, so that's dW dt and that's positive. You just plug in those values into the formula. So I've done that here and you could check your answers, but I want to go ahead and move on to the next question. So the next question, we're talking about a right triangle. They do give you 2 of the side lengths, but those are changing, so we're not really going to worry about those just yet. Right formulas for the area and the hypotenuse. And then talk about their changes. So let's look and see here. So the area of a right triangle is 1/2 base times height. So the change in area, this is one of the formulas you're supposed to take the derivative of in class today with respect to time. This would be dA dt. And we have to do the product rule for 1/2 b times h. So 1/2 b is first, times the derivative of h, plus h times the derivative of 1/2 b. All right. So this is our change of area formula. First d last, right? First is 1/2 b, last is h, so dH dt, plus last, that's h, times the derivative of 1/2 b, that's just 1/2 dB dt. And then we have the hypotenuse formula, or the Pythagorean theorem, my favorite derivative. You can't tell me this isn't Pythagorean or this isn't Shakespearean whenever you say it. It's 2a dA dt plus 2b dB dt equals 2c dC dt, right? So that's our change of hypotenuse formula. Okay, so in our triangle, right, and if you do the Pythagorean theorem, the hypotenuse would be 50 for right now. The short side is increasing at 3 inches per second. So I'm going to call that, this short side here, the base, and the long side, the height. All right, so dB dt and dH dt. So the short side, the base, I'm going to call that dB dt is 3 inches per second. And the long side, I'll call that the height. And it really doesn't matter which one you call the base and the height. If you want to try it out, you can switch which ones you called base and height and see if you get the same answers as me. The long side is increasing 5 inches per second. And I'm calling the short side the base and the long side the height. So for change of area, we just plug into that dA dt formula. For change of area, we would have 1/2 the base times the rate of change of the height plus the height times 1/2 the rate of change of the base. So this would be 75 plus 60. That would be 135 inches squared per second. For the rate of change of the hypotenuse, we plug into our change of hypotenuse formula, and we would have, instead of calling them base and height, we would call them A, B, and C. It really doesn't matter which one you call A, which one you call B, which one you call, well, the C does matter. The C has to be the hypotenuse. So I'll call 30 the A side, 40 the B side, and 50 the C side. Keep in mind that B means something different here. It's just a side. It's not necessarily the base. So for change of hypotenuse, we do 2 times A times dA dt, right? And the short side, that's what we're calling A, is increasing 3 inches per second, plus 2 times B, which is 40, times dB dt, which was 5, equals 2 times C, the hypotenuse, which is 50, times dC dt. So you're going to figure out what this is, then divide it by 100, right, to solve for dC dt. So this would be 180 plus 400, so 580 divided by 100. This would be 5.8 inches per second. All right. All right, so you can try this other one. We will work the examples on the back in class tomorrow, but go ahead and try part B here. I'll write the answers. You can see if you got them right. All right, so you should have gotten for the change of area. You're plugging in same formula, but notice that the rate of change of the base and the rate of change of the height changed. And so it made the total change in area change. It's just minus 15 inches squared per second. Same thing when you came to do the change of hypotenuse. Same formula, we're plugging in the same stuff, but notice that these two numbers changed. The dA dt and the dB dt, and so it caused your answer to change. The change of hypotenuse is negative 2.2 inches per second. So go back, make sure that you've worked all 3 of these examples, watch the video again if you need to, but make sure you try all of them, and then come with questions to class tomorrow, and we'll talk about this some more.